All right, so welcome back, everyone. And next up, we've got Carla Groenland from Utrecht, and she's going to talk about graph reconstruction from small cards. So, all yours.
Thank you very much for the introduction. So yeah, I'm very happy to get interrupted during this talk, so please ask me lots of questions. Everything I'm talking about is joint work with Tom Johnston, Alex Scott, and Jane Tan. And I'll be talking about one of my favorite topics, which is about graph reconstruction. So let me first introduce to you what this is about. So we're giving a deck of cards. So an example here is given above for this nice graph over here. And how do we attain this? Well, we remove one vertex at a time and then look at the induced subgraph that remains. So we remove the vertex and also any incident edges. And an important thing to note here is that the vertices are not labeled. Otherwise, it would have been quite easy to retrieve back the original graph. But in this case, when we get these snapshots, these 4 of them, we can still get back the original graph because we can say, oh, well, there has to be a triangle in there somewhere. And then maybe we can start doing some degree counting or something to figure out that there's still one vertex that has a single edge to this triangle. So now the question becomes, can we always do this? Do the strict induced subgraphs of a graph determine a graph? So we're given a graph without multiple edges, without self-loops, without labels. And I'll denote G minus V for the card of the vertex V. So we've removed V and all edges incident with V. And instead of n vertices, we now have n minus 1 vertices. Now we get the multiset of cards. So we allow multiples, as we saw on the previous slide. And we want to know if, given this stack of cards, can we get back the original graph? So this will always be up to isomorphism. So we say that the graph is reconstructible if every graph with the same deck has to be isomorphic to it. So now the question is, can we always do this? Well, there's one bit of a silly counterexample. So I don't know if someone wants to have a go of a silly example for which we can't do this. Think small.
If you only have 2 vertices?
Yeah, exactly. So if you only have 2 vertices, then you always see a single vertex. So we don't really know if the edge between them is there or not, because for both of those graphs, we only see 2 single vertices. But a very old conjecture from Kelly and Ulam says that as soon as we have 3 vertices, we can always reconstruct the graph. So this is a very nice conjecture. It's mentioned in multiple surveys and books, and it's not something to spend your whole PhD on. But I'll tell you about some sort of related questions which I have spent quite a big part of my PhD on, which they're in the same topic, but reasonably easier. So there's, instead of reconstructing any graph, you can also place some assumptions on the graph. So for example, if you know that the graph is regular or it's a tree, then it suddenly becomes a lot easier. And in fact, almost every graph is very easy to reconstruct. So for almost any graph, you only need 3 cards. So in this random graph model G and P, you just need 3 cards with high probability. And there's also a variant where instead of
One question. So by P fixed, you mean P constant or you mean like any P?
Yeah, so for P constant, you only need 3 cards. Okay. And if it's known for any P, but you might need more cards if your P is within a certain range.
Okay. Yeah. Cool, thanks.
That's not, for a certain range of values of P, the exact number of cards that needed is open. But yeah, so people have also considered some other variants, but yeah, a lot of them turn out to be false. But there's one simpler version, which is maybe also interesting, where instead of removing 1 vertex at a time, we remove 1 edge at a time. So this is a bit of background on the general problem. And what we'll be interested in is still reconstructing some information about the graph. So we say that the graph parameter is reconstructible if its value only depends on the deck. So what does that mean? Well, suppose we want to reconstruct a number of edges in the graph. We are given the deck of cards, so we can compute the number of edges on any card. And if we now think about it, well, each edge appears on almost every card, apart from two specific cards, namely from its two endpoints. So if we do the counting, we see that this quantity here on the left-hand side, which we can get from the deck, this will actually be equal to a quantity that we may be interested in times something we know, because we know the number of vertices. So we can compute this thing and we compute the thing on the left-hand side, and from that we can get the number of edges. And now that we have the number of edges, we can also start trying to get things like the degree sequence. So I've got a little picture here. We have a graph G and we take any vertex V away from it, then we have this sort of blue graph remaining. And which are the edges that are not present? Well, those are exactly the edges that were incident with the vertex V. So what does that tell us? Well, it tells us that the degree of the vertex V is the total number of edges in the graph minus the number of edges on the card. These green edges, that's the degree of the vertex. So after we have this if we do this for every single vertex, then from there we can get back to the degree sequence. And this also now shows you maybe why, for example, regular graphs are easy to reconstruct. So we know the degree sequences, and now there's just some vertices which have a degree missing, and phi just needs to be put in those spots. And in similar ways, we can also compute all kinds of information about the graph. Okay, so the two kind of setups that I looked at, instead of getting the whole deck, we're going to get a bit less information. So originally, we're going to get all induced subgraphs on n-1 vertices. So one type of situation that I've looked at, which I won't talk about in this talk, is a partial deck setup. So instead of getting all the cards, we get strictly less cards, but still we see these really big subgraphs. And the second natural question is, what if we make the order of the subgraph smaller? So here I'm introducing the L deck, which is the multiset of all induced subgraphs of order L. And again, it's quite a natural question of how small can you make these subgraphs and still determine properties of the graph? So I think that's quite a natural question in its own right. Okay, so let me first tell you a little bit about how to get subgraph counts. So there's something called Kelly's lemma, and this basically tells you how to get the number of induced subgraphs in the graph from the LDEC. So Kelly's lemma was stated in the original setup, but you can easily adjust the proof to this case. And we do a very similar thing as we did for the edges. So we want to get, I think this went a bit wrong with the indices. Well, we want to get the number of induced subgraphs H in the graph G. And now the only thing we have are again these cards. So we're just going to count the number of H subgraphs in the things that we do have, just like we did for the edges. So by this assumption that L is at least the number of vertices of H, that tells us exactly that it does fit on a card. So if it does fit on a card, how many cards is it going to fit on here? Well, we need to put in the we fix the vertices of the copy itself, and now we need to pick L minus P minus H vertices more from the remaining vertices of the graph. So this thing here was exactly the same as on the previous slides. We had n-2 because that was that was the remaining thing there. So there's some kind of way that we can get these sort of induced subgraph counts. So why do we care about this? Well, first of all, this makes it possible to get smaller decks from bigger decks, because we can, from the deck of induced subgraphs of size L, we can get all the sort of smaller subgraphs from there. So we can get these L prime decks for L prime at most L. So now it starts making sense to investigate what is the smallest size we can get so that we can reconstruct something from the L deck. And let me remark here maybe as well that this variant of Kelly's lemma, so it's also maybe tempting to do this in the partial deck setup, but there it becomes a lot more difficult. So even for reconstructing the number of edges, even with 2 cards missing, it was like a paper of someone. And the best known bounds are still quite far away from each other. So this sort of counting thing in the small card setup, it works very nicely, but in the setup where we remove some cards, this becomes a lot more difficult problem. Okay, so there are some examples of some results that are known about this. So some things that people have looked at are, for example, reconstructing the degree sequence. So these are sort of the best known bounds for this, and recognizing whether or not the graph is connected. So these upper bounds here are two of our results. And I won't talk much about this in this talk. I want to talk about a different result later on. But just to give you some intuition about this small card setup, I just wanted to run you through an example for why these bounds might get so large. So what I'm going to show to you quickly is a result from Spinoza and West, that if we take these two graphs, that they actually have the same n/2 tag. So I won't show you it exactly, I'll just show it in a little example. But this is just to show that even for easy things like seeing if the graph is connected or not, we might need quite large subgraphs in order to determine this, even asymptotically. So this notation here just means disjoint union. So I've drawn an example here for n is 6. Here we have a 4 cycle and a path of length 2, and here we have a path of length 6. And the claim is that all the small cards counts are the same for these two graphs. And clearly this one on the top is not connected, but the one in the bottom is. So what does this actually mean, these cards? Well, we can first count the numbers of independent sets of size 3. And if we do a little counting here, we see that there's 4 for this one, and here there's also 4 options. There's no triangles in either of them, and now we just have to count one of the other two. So here I've counted the number of subgraphs isomorphic to the path of length 2, and we see here that here it has 2 of these, and it can sort of wrap around. And here on the top, we can wrap it around here. So note that this is really about induced subgraph counts. So we know that the remaining entries need to go to the last option. Okay, so hopefully the setup of the LDAC is a bit clearer now. And yeah, so we saw previously that for some of these properties, we could actually remove a linear size of the vertices, but in general this is not possible. So I think, yeah, that's quite a natural question, but Needle solved this in 1992. So in fact, there are non-isomorphic graphs on n vertices who have the exact same subgraph counts for all subgraphs, which are getting asymptotically close to n. So for any epsilon, we can get the same 1 minus epsilon times n deck. And the conjecture that Needle made as well in a different paper is that for trees, the situation is actually very different, that there you can remove a linear chunk of the vertices, and yet an exact value here as well. So it turns out that for recognizing whether a graph is a tree, the bound that Needle proposed is correct. So for some small values of n, it's known to be incorrect. And the best other result that was known about it was from Giles, which showed that you can look at the subgraphs where instead of removing one vertex, you can remove 2 vertices. But not since then, there is no improvement on this bound of n minus 2. So what we looked at is trying to reconstruct the trees from the LDAC. And what we found out is that actually this conjecture from Needle is, in spirit, it's sort of true. So we can indeed remove a linear chunk of the vertices. So this bound is still probably incorrect, but like that you can do better than this 8/9. But it does bring us a lot closer to sort of the true answer, because there is this lower bound. Needle did have a lower bound of n/2 as well. So that this sort of gives the right asymptotics, but not with the right constant. So this is the result I wanted to tell you something about today. Are there any questions about what any of the terms mean? So there's a couple of sort of new ideas that we introduce in our work. I think one sort of picture I like to have in mind a little bit is that one thing which is very nice to have is if there's some unique little pattern on your graph, because then that's recognizable on the cards and you can start building up from there. And in our case, we sort of keep looking at a longest path. So it doesn't have to be unique. In fact, we have to account for the fact that there might be many longest paths. But that might be easy to first maybe think a little bit about the case where this is the case, and then there's some structures already present, and we can start growing the rest of the tree from there. And the rest of it mainly consists of a bunch of clever counting results. There's two different types of counting results that I'll tell you about. And the first is something for counting maximal subgraphs, which was something that Bondi and Hamming already did in 1977. And the other one is a new result about counting subgraphs with certain specific types of neighborhoods that I'll tell you a bit about now. So suppose that we can recognize some kind of longest path on the card. Then we already suppose that there's a unique longest path in our graph. So we can suppose that it fits on our card, then we can get the count from Kelly's lemma, and we can see that there's only one of them. And now we can just look at all the cards which contain this longest path. And from there we can start trying to build off the branches that hang off this path. And we look at it corresponding from the center. So suppose that we were able to reconstruct the counts for these kinds of graphs. So suppose we knew the number of ones for which we have this long graph, and then in the middle, there's a copy of A hanging off it. And we know the number of them which we have such a long path, and in the middle, there's a B hanging off it. And we know the ones for which there's some super long paths, and yeah, in this, there's a copy of E hanging off the center, and the path runs through this. If we have sort of all this information, then from these counts, we can actually reconstruct the original graph. So there's a bit more technicalities here, of course, because there might not be a unique longest path, but this is sort of the general idea for one of the cases in our proofs, is to do this construction. So what we now want to do is we want to be able to reconstruct these kinds of things, like this is long path with something hanging off it. And we will do this by viewing this as a maximal subgraph. So there's a counting result from Bondi and Hemminger. And in our case, we're going to start with the class of all n-vertex graphs. And now our class of graphs where we want to do counting for are a path with something hanging off the center. This class of F will exactly be these kinds of graphs. And the conditions in our lemma, what we need to ensure, well, the first thing is that for all possible things from my graph class F, they need to fit on the card. So that this tells us that the number of vertices need to be at most L. And the second thing that needs to be true, which is the more tricky one, is that each such graph needs to be contained in a unique maximal subgraph. So this is the case in our setup here, where we can start looking for these kinds of things. And if all of these things of this form will fit on our card, then each one in our graph will be in a unique maximal one. For example, there might be sort of sub-things of this A in here, but for them, the maximal one will be this branch with A hanging off it. So this is the second condition to ensure this. This is why we sort of needed to anchor the graph. So now if we have these conditions, then what the lemma tells us is that we can reconstruct a number of maximal copies of F in G. So those will actually be our branches. And we only need to have the cards in the L deck that contain such a subgraph. So we only need to look at the cards which contain a longest path. So in fact, this will take care of of our problem for us for a whole range of values of L. There's some things that we need, like we need the longest path can't be too long, for example, because otherwise it already takes up a lot of space on our cards and it becomes very difficult to fit the whole graph F on the cards. And there's a few more tricks that we need to do here. But this is sort of the main idea behind our approach of handling the case where the longest path is not too long. So what do we do for the trees which do consist of a very long path? The main idea here is that we sort of break this path into two in the middle, and now we want to sort of find out that there's a copy of the left-hand graph and there's a copy of the bottom graph, and the fact that these two things are disjoint and that they need to be glued by some kind of edge. So this is sort of the picture to have in mind. This is what we want to do. And in order to know where to glue, what we're going to do is we're going to count the number of copies of graphs with labeled neighborhoods. So what do I mean here? Suppose that my entire graph consists of the black and the purple vertices and the edges that are drawn. Now, in this graph, there's a subgraph H here, and it has a specific neighborhood which takes this form. So we kind of want to do counting for sort of the one ball of this graph. And we also want to know where in this one ball my copy is present. And in particular, we're able to count the number of copies for which we have some kind of half-long path here, for which we know that the whole one neighborhood of this path is only a single edge. So that's sort of the information we want to know in the end. Because if you know that there's a copy of this graph here at the top, for which the neighborhood is only a single edge, then we already know that there's some kind of situation like this. You don't necessarily know what other graphs it's going to glue, but we know that the situation already looks something like this. Okay, so how do we count these kinds of neighborhoods? What can we do for that? So there's again an issue that we need to make sure that the one balls all fit on the card. But after that, if it's the case that the one balls all fit on the cards, then we can in fact we can do this counting. So to make this really sort of official and sort of work out this notion of labeled, it becomes a little bit of a technical mess. But we are able to do this in sort of a more general form as well, where instead of looking at labeled neighborhoods, we look also at vertices distance 2 and 3, etc. But yeah, this allows us to so basically the thing that we need to check is that in order to get the number of counts of H with this neighborhood, we need to check that H doesn't appear somewhere else in the graph with a super big neighborhood. And as soon as that's the case, we can get the counts. So let me maybe just give you a really brief idea of how this is done. So it's basically a sort of inclusion-exclusion argument. So let's first consider the case for which it's the biggest neighborhood H has anywhere in the graph. So now if we count the number of copies of H with that neighborhood, and it's the very biggest neighborhood that H can have, so we can see that it's the biggest one, right? So if we know that they all fit nicely on the cards, and we can see that there's one for which the one ball takes size 10, and there's no copy for which the one ball takes size 11, then 10 was the biggest one. So we can just count those, and we know that that's the correct answer. But now when we start counting the next ones, it might have happened that actually the neighborhood was bigger, but we didn't really see it yet on the card because some of its other neighbors got removed. So here what we need to do is we need to take into account that some of the things that we're counting are actually coming from subgraphs of things we've counted before already, from sort of larger examples. So we need to keep removing those from our counts, and working this out actually allows you to get all the counts. Just see what so this is in the end what we do for reconstructing trees. And I just wanted to mention one more sort of counting type result that we can get. So these are sort of the two counting results I mentioned before, and there's Kelly's lemma, and there's one other type of counting that we've done for this problem of recognizing connectivity. So in this case, this is a way of counting degrees of a component. So if we look at this graph over here, then we see that there's a graph that looks like this over here, which doesn't have any neighbors. So it sort of has degree 0. Where there's also a graph in blue over here, and it has sort of 3 neighbors, which are circled in green. And the idea for our connectivity approach is also to start counting the degree sequences of components. And then we just need to know, are there any subgraphs for which the degree of the component is equal to 0? So that maybe tells you why we've been able to sort of do connectivity recognition and degree sequence. And we get this in the end from a bit of a maybe intimidating result. So what does this result tells us? Well, suppose that we know that a bunch of these binomial sums are equal. One way to get this is if we took beta to be the same as alpha, or we just take some kind of permutation of alpha. But what the result tells us is that if they're not a permutation of each other, then knowing these kinds of sums allows us to get back the sequence of integers. And how many of these sort of moments do we need to be equal? Well, at most, some number that depends on our entries. So one reason why I find this result quite cool is that in the end, this result is proven by another intimidating looking theorem that I won't talk much about the proof today, but in the end, you can prove this theorem, this lemma above, from a theorem about complex polynomials. And then in the end, we can use this lemma again to say something about graph reconstruction. So I think that's quite cool because you wouldn't really expect in the graph reconstruction setup that some kind of theorem that looks like this would be applicable. So let me just tell you a little bit about how we do this. And I think it's easiest to see this for the degree sequence one, because that's a bit less complicated. So to remind you of the setup, we are given the multiset of all induced subgraphs of order L. And we want to show that whenever two graphs have the same LDEC, that they have this, that the corresponding graphs need to have the same degree sequence. And then if that's the case, we can say that the whatever value we prove this for DEC is sufficient to determine the degree sequence. We always need n at least 3 because, yeah, we don't want it to be a single edge. So for there, we already know that you can't do it. Okay, so what we in the end want to get to is this lemma about binomial coefficients. And it turns out useful for that to reconstruct the number of subgraphs isomorphic to the star. So this is a special case of Kelly's lemma. So it's something that we saw before. So what we do is we just count the number of copies of the star that appear on the cards, and we sum them up over the deck. And now we know that each copy, how often does it appear? Well, the graph needs to contain this copy, and then for the card, we still need to fill it up to an L card. So we choose L minus 4 vertices from the remaining n minus 4 vertices in the graph. And that gives us the number of times that each copy appears on the cards. So using this thing on the left-hand side and this thing, we can actually get these counts. And it turns out that these counts, they exactly give us these sort of binomial sums that we're interested in. Because if we look at any vertex V, how often does it appear as the head of a star? Well, let's assume that the star is not an edge or a single vertex. So we just, it needs to have a large enough neighborhood. And if it has 5 neighbors, then it appears as the head 5 choose 3 times. So it's degree choose the size of the star that we want to get. And then that means that the number of subgraphs isomorphic to the star, it actually gives us this sum of binomial coefficients that we were able to say something about, where these degrees is something that we want to know. We want to get the degree sequence. So this is just repeated here. If we know that 2 vertices have the same LDEC, then it must be the case that these binomial sums are all equal for all the values that we can reconstruct the star counts. When can we reconstruct the star counts? Well, we need the star to fit on the card. So we can do it as long as the star fits on the card. So that depends on L. So now, if G and H didn't have the same degree sequence, then if we take these two things as their sequences, then they're not related by a permutation. If they're not the same degree sequence, then these alpha and beta won't be the same up to a permutation. But at the same time, we just found that these binomial sums were all equal. And the lemma then tells us that, in fact, we can retrieve the alpha I and the beta I values. So this shows us that, in fact, this shows us that this L cannot have been. So we can do it by the lemma if this L was sort of larger than this, but because we know that they're not related by permutation, it must be the case that we can't reconstruct too many of these sums. So this tells us that we can get the degree sequence as soon as we have more than this as sort of space on our card. Okay. So let me maybe skip over this, and let me just finish with some open questions. So there's still some gaps for trees and for the degree sequence and for connectivity. And there's also a bunch of interesting questions in this partial deck setup. So the subgraph counts is an interesting one there. So already for the number of edges and the number of triangles, this is open. And also for things like reconstructing the degree sequence. And another, which I think is quite an interesting question, is whether you can get sort of an analog of Needle's result in this setup. So can you get graphs which have a lot of subgraphs of size n-1 in common, but which are not isomorphic? And two final questions, which I think are quite interesting, is can we reconstruct in general, just so from big cards and big decks, the class of planar graphs or the graphs of maximum degree 4 or 3? But yeah, these are probably quite hard questions, but it's somewhat interesting that these still remain open. Yeah, so thank you very much for your attention.
Right, thank you, Carla, and let's all unmute ourselves and give a round of applause for her. So are there any questions?
What do Needle's counterexample graphs sort of look like?
So they're just sort of caterpillars where you sort of end up putting the neighbor slightly differently in different positions. Yeah. But there's this, yeah, for small n, there's a slightly better example that Tom found by computer search. So for I don't remember the exact value of n, but for really small n, you can do slightly better than the construction of Needle. But we don't know if that generalizes, because it's a bit more unwieldy, I guess.
I have a small question. So I think at the beginning you mentioned the random graph GNP, and you said that 3 cards suffice to reconstruct that. I assume you mean that there exist 3 nice cards.
Any 3 cards.
Actually, any 3 cards.
Yeah.
So if you restrict to random graphs, the partial deck question becomes super
trivial. Yeah.
Easy. Okay.
Yeah, whereas just getting the number of edges for any graph was like a research paper to do that with 2 cards missing. So yeah, it's somewhat interesting that, yeah, even with like 2 or 3 cards missing, we don't know how to reconstruct the degree sequence. But if you give any 3 cards in general, that should be enough to just get the whole graph. I mean, not for all graphs, but for most graphs. But also, yeah, in general, it's also not very well understood how many cards you would need. So I had one example, which I skipped over in my slide. which is sort of these two. So this is sort of the best known example for how many cards you can have in common. So the top and the bottom graph, they're non-isomorphic, but they have a lot of cards in common. And the number of cards that they have in common is just 2/3. So yeah, so instead of needing 3 cards, you would need to have more than 2/3 of the cards. If you give sort of bad choices of the cards. But I think also for giving any cards, there are sort of lower bounds that are linear in n. But beating this 2/3 is also open still. I think that would also be quite interesting to get 2 graphs with a lot of common cards.
Carla, I also had a small question.
Yeah.
Now that, well, I don't know how much does it make sense, but what if you're given a random random subset of cards?
A random subset of cards?
Yeah, like you have your graph, and then out of n cards, you're given like randomly half of all the cards. So what?
So I mean,
not the worst choice, but a
random choice.
Yeah.
Yeah. So the.
Is it in any settings like the edges, for example, number of edges and so on?
For reconstructing the number of edges, if you get a random set of cards. Oh, yeah. I guess that might allow you more easily to get good estimates on the number of edges just by summing again. But I haven't tried that. But because of course reconstructing it would need to be for a setup where you just want to get some information, because in general we know that's there's a lot of things we can't do even if we get the whole deck. But for getting the number of edges, maybe if you sum the number of edges on the random cards, I don't know how good of an estimate this would give, but
or the degrees, well, no, degree sequence, I don't know. But anyway, I was just wondering if this setup is meaningful, because if you have random graphs, then you can reconstruct from any 3 cards. So I don't know. Can you get something in between, like for random cards, but with arbitrary graphs?
Yeah. I mean, for the lower bound examples that I know of course, if you get a random selection of cards, then it's quite likely that you'll be able to tell them apart.
Yeah. This is.
But there are some, I think there are some examples as well where they show you that any collection of n over 2 cards or something doesn't suffice. But I'm not completely sure of that. I haven't really looked at. So there's sort of existential and universal reconstruction numbers, they're called.
Okay. So that's.
Yeah. So if one of these 2 is the ones that we're looking at with you can get the worst case, and the other one is sort of the best case one, where you can choose your collection of cards to be something you like. And people Mervelt and other people have studied this. And I seem to remember that there was like a bound of n over 2 for that, but I'm not absolutely sure for that.
Okay, cool, thanks.
Are there any more questions?
So now that Andre asked this, I want to continue on that. So this reminded me a bit of kind of or one game that is played in some similar setting, where you actually would imagine, say, that 2 players alternately playing cards, or one player takes one and then the other takes another one, and so on. Like that, where you would one player would want to get a set of cards that uniquely determine a graph, or say that they somehow get something meaningful out of the set of cards. Either they uniquely determine, that would probably be the first choice, but maybe also to otherwise get some kind of meaningful property.
Yeah, I don't think I've seen this much, but it might have been studied for some specific case. I guess one of the hard things here is that, yeah, even some very easy things are quite poorly understood. So it's not that clear what the collection of good edges would be, good cards would be. So I feel like this is maybe sort of a way to make your life even harder, whereas we already don't really.
So there's no something like say also if you have a larger set of all possible cards and then trying to get some kind of contradicting set of cards or something like that one of the opponents would try to do, or would there be some kind of local result that gives you a contradiction in terms of say if you would have a set of all possible induced graphs and then you're picking cards until there is no possibility of that being a set of any graph or something like that.
Oh, okay. You mean you keep selecting them, and then at some point there might not be any graphs that correspond to it, or recognizing whether.
For example, yeah, I was just commenting on asking if there is a possible, then if there is some kind of local or any kind of criteria that that would give that.
Yeah, I don't really know of any
property.
criteria. There are some people that have looked at this problem of like it's called legitimate deck problem. So you want to know, given a set of cards, is there a graph that corresponds to that? And that's sort of like a question which is basically equally hard as cross isomorphism. There's some kind of reduction between those two. And yeah, there's also one setup which I looked at the start of my PhD, which was, I thought, really fun, which is where instead of getting a partial deck, you get a false deck. So some cards have been maliciously replaced by different cards to try and fool you. But this is actually, yeah, at least for a lot of things, basically equivalent to getting a partial deck. Because there's always, if you get two cards which have the same sort of wrong deck, then they must also have quite large partial decks which are the same. So if there had been sort of 3 cards that can have been meddled with, then they have all but 6 of their cards in common. So these two setups are actually a bit the same. But I thought that was kind of a cute setup. So it was a bit of a shame that there was this. Because yeah, I had a very nice argument for extending some result there without this easy reduction. But yeah, it's but yeah, I think that your sort of proposed game makes sense, but also I wouldn't necessarily immediately know of an interesting result to prove in that direction or an interesting type of question to look at, because I think it's, yeah, I feel like we don't know yet much about sort of the general case to start. I feel like it's just like a more difficult, you need to understand even more about the structure, I feel, to really analyze winning strategies for these games and stuff like this, or like how many cards can they both claim and stuff. That, yeah, I imagine that only makes things more difficult.
Okay, thanks. Yeah, I'll take a look at these things that you refer to. Yeah, thanks.
Yeah.
Okay, so next up we have a somewhat long break, and we're going to continue at 5:30. Of course, everyone feel free to stay and we can keep talking to the speakers, and if we have any more questions, we can ask them. But before that, I propose that we just unmute ourselves and thank all 3 speakers so far for their talks.